Jean-Christophe from Lyon, and he's going to talk about the qualitative homogenization of interacting particle systems.
Thank you. I thought you wanted to record, no? I don't know if that's.
Oh yeah, but the IMPA staff is doing everything.
Okay, sorry. Yeah, so thank you very much for the invitation. So yeah, indeed, I want to talk about interacting particle systems. And so things are going to happen on ZD or on RD, so Euclidean space. And we will have a cloud of particles, which each individually is trying to do a diffusion or a random walk. And the way this diffusion or random walk evolves is going to be influenced by the local configuration of neighboring particles. And so we're going to give a macroscopic description of the dynamics. And what we want to understand is the large-scale behavior of this cloud of particles. So it's in fact well understood that for the models I'm going to talk about, if you look at them over large scales, then this cloud of particles is going to have some effective behavior, like which, the density of particles is going to evolve according to some diffusive equation. But the focus of our work is going to be on trying to devise quantitative estimates for this statement. So instead of shooting for the fact that in the limit of infinitely large scales, this cloud of particle behaves diffusively, we want to say, how good this result is, like how close to the limit we are when we are in finite volume. And we are not yet at the level of quantifying the result I said in words per se, but we have some intermediate result which we believe can lead us to that point. So that's the goal of the talk, is to make this sort of information on the large-scale behavior of particle systems quantitative, like to find explicit bounds on these things. And the way we are going to approach this draws from ideas that come from a somewhat different topic. It comes from things we have worked on in the homogenization of elliptic equations with random coefficients. And if you're a probabilist, you probably prefer the language that talks about diffusions in random environments. Yeah, so there is a fairly rich space of models that I'm going to at least touch upon a little bit during this talk. So let me try to kind of map out which models we can talk about. So models that I want to talk about today, where we can make them discrete on ZD or continuous, like they happen on RD. They can be about these random walks in random environments. This is the inspiration this is where we take our inspiration from, or these elliptic equations with random coefficients. Or it can be about interacting particle systems, which is our true goal for today. And you can think about the problem or talk about the problem through either probabilistic language or PD language. Okay, and maybe you have a preference in this space of choices. Maybe you like discrete random walks and you like to talk about them with probabilistic words. Today we're going to, at least our ultimate goal is to describe an interacting particle system. It so happens that we chose to talk about one which is in continuous space, and possibly we employ more of the PD type language in this talk. But in order to try to clarify analogies and perhaps also to explain things in a simpler setting, I will also touch upon this random walk in random environment thing, or elliptic equations with random coefficients. Is it okay? Is the plan kind of clear? So first, I'm going to give some exposition of what we have understood in the context of random walks in random environments, or elliptic equations with random coefficients. And then in the second part of the talk, I'm going to try to describe how we adapted some of these ideas to the setting of interacting particle systems. Does that make sense? Is it all good? Okay. Yeah, so by the way, I haven't said it yet, but I really appreciate questions. So feel free to interrupt whenever something is not clear, or whenever you want to add something to what I say. I really appreciate it. All right, so first part is going to be random walks in random environments, or slash elliptic equations with random coefficients. So just to make sure we are all starting from the same from the same basis, let's say, let's imagine first that we try to devise our random walk on ZD. So on ZD, we would, in order to define the model, we would put random variables on the edges of the graph. So that would be our random environment. So for instance, we could choose them to be IID, and it's they are let's say uniformly bounded away from 0 and infinity. And then the work we would want to study would be defined by specifying that the transition probability is given by these weights. Okay, so this is omega xy dt if x and y are neighbors. Otherwise, it's a little law of dt. Okay, for x and y being neighbors. And yeah, so I should have said, so this is a notation for the set of edges of the graph. And one key aspect of this model is that I assume that the edges are not oriented. So omega of xy is the same as omega of yx. Okay, and so you see that the jump rates, so the jump rate from x to y is the same as the jump rate from y to x. In particular, the counting measure, the measure that gives mass 1 to each site on ZD, is going to be reversible for the dynamics. Okay, so let's say counting measure is reversible. So sometimes people call this model the random conductance model, or random walk in random conductances. Okay, so this reversibility aspect is really fundamental to the model. It will influence a lot of how we approach the model. Okay, and if this is perhaps the more probabilistic description, but if you want to think in more PD terms, you want to talk about the generator of this Markov process, and it will take this form. Okay, so sum over y neighboring x of omega xy f of y minus f of x. Okay, and the fact that the counting measure is reversible, you can read it off from the generator as well, because this generator will be symmetric with respect to this measure. Okay, and now so now we start to our travel through the space of models. So this was discrete random walk in random environment, maybe a probabilistic view and a more PD view. But yeah, I want to bring us to the continuous world now, and I will then stay only discussing continuous models after that. So yeah, if I want to make a diffusion which looks like this, I need to preserve this reversibility aspect. Okay, so maybe I'm not going to write the Ito formula or something. I'm just going to write this PD perspective. You know, what is the generator that corresponds to a diffusion in random environment that looks like this, except it's in continuous space. So in continuous space. So again, we're going to give ourselves something that describes the random environment. So it's going to be a mapping from RD to the space of symmetric matrices. So let me write like this for the space of symmetric matrices. And again, you know, they're going to be positive semi-definite and away from 0 and infinity, let's say. And the generator, the operator that corresponds in continuous space to the discrete thing I wrote above is, well, let me write LF of X, is the divergence of A gradient of F, okay, computing at X. Okay, so you see that, you know, if you imagine you want to test this operator against another function and integrate against the Lebesgue measure, you can do an integration by parts, and you see that at least formally this operator is symmetric with respect to the Lebesgue measure. Okay, and this is the key property that we want to preserve from the discrete model. You know, the discrete model had this reversibility property with respect to the counting measure, and in continuous space we want reversibility with respect to the Lebesgue measure. Okay, and asking for that imposes that the generator has this form. We say it's in divergence form. Okay, and this matrix A, you can think of it as being the local diffusivity of your diffusivity of your random diffusion. Okay, I'm perhaps lacking words for how to speak about it properly. So for instance, if A of X is 2 in some region, then your random walk will behave like a Brownian motion with variance 2. And if A of X is 1/2 in some other region, your random walk will behave like Brownian motion with a variance of 1/2. And okay, maybe there's always a factor of 1/2 between the operator, the Laplacian, and the Brownian motion. So maybe I'm off by a factor of 1/2. But okay, that's okay. I hope you get the idea. Are things clear so far? So just to perhaps clarify the, yes, is there a question?
Yeah, maybe just I think I've seen this many times, but I never really understood. Where is it? Okay, where is it the analog? Where should you put A inside here instead of considering, I don't know, something like A times Laplacian? Or maybe,
yeah. So if you do A times Laplacian in the discrete, it corresponds to what people call balance walks. So if you do a balanced walk, then your random walk is a martingale as is. Like so you know, at each point is going to decide equally with equal probability to go to the left or to the right. It's just it can have some, you know, maybe there's different probabilities in the horizontal direction or in the vertical direction, but it's always balanced, and this would correspond to having you know, some matrix times the Laplacian or some coefficient times the Laplacian. This would be a time change of Brownian motion. It would be also a you know, a diffusion with something that is a martingale. So it does not look like the discrete model I wrote above.
Okay.
You see, it's the analog of another discrete model. Does that make sense? Or?
Yes. Thanks.
So yeah, I wrote explicitly the assumption of, you know, being bounded away from 0 and infinity. This is for matrices, so it's, you know, the quadratic forms satisfies this sort of bounds. And if we want to make, if we want to say quantitative things, it's important that we, okay, so first I should say, we want to assume that this coefficient field, so it's random, but we want to assume that the statistics are the same everywhere in space. So, you know, we want to assume that it's the law of this thing does not change when we shift the coefficient field. So it's, in other words, it's a stationary random field. Okay, so A, let's say stationary random. Okay, so for instance, if you're just throwing balls in your medium, I want that you throw balls with the same density everywhere. I don't want that you change the law according to the position. And in order to make things quantitative, I also want to assume some decorrelation properties. So maybe for simplicity, I will assume that A has a finite range of dependence. Okay, and now we want to study the corresponding diffusion, and we want to say that over a large scale, it looks like a Brownian motion. Okay, so it's not obvious. For instance, in this conversation with Hubert, I mentioned that our random walk or our diffusion is not a martingale as we have defined it. So if you're in your discrete model, if you see that a point and this omega e is very, very large, you have a very high chance to go to the right. So you see that the walk is not a martingale on its own. So in particular, it's not super obvious how to show that the random walk will look like a Brownian motion over large scales. But now, if you ask this question in some PD style, it looks like this. So you're going to say, so let's say PD question. So instead of studying the random walk, you can look at solutions of equations that involve this operator and which are posed over large scales. So let's say we solve some equation. So sometimes I fancy to put a minus in front of the operator, but don't pay any attention to that. It makes me happy for some reason. I got used to this. It's hard to avoid, but anyway, it's not important. Okay, so we would take a very, very large domain, much larger than the scale of correlations of the coefficients. Let's call it U. It's extremely, extremely large. And we impose some boundary condition on, let's say, G on the boundary, which is not a crazy boundary condition. It's kind of smooth in some sense. And we are trying to solve for this. So if you think in terms of heat conduction, it's like you impose a temperature profile at the boundary of your domain, and you're trying to calculate the equilibrium temperature inside the domain. And the diffusion of heat is governed by this matrix A of X locally. Okay, so that's what this equation describes. And if the domain is very, very large, then maybe there is some sort of averaging of the coefficients that happens, just like we expect the random walk to look like a Brownian motion over large scales. So maybe there's some effective matrix, let's call it A bar, such that the solution to the problem above, like with the U, looks like a solution where, of the same sort of problem, except that I have replaced this matrix A of X by A bar. So here, there's a crucial thing that is going on, which is not very clear from my notation, but the crucial thing is that here, A, when I write A, I mean A of X. Okay, this is A of X. It's just that I don't write the variable. While here, A bar is just a fixed matrix. Okay, it's constant in space and it's deterministic. Okay, so A bar constant in space and deterministic. Okay, so what we would like to say is that when the domain is very large and G is sufficiently smooth, we have that U is approximately equal to U bar in some sense. Okay, and this, you can think of this as some sort of averaging phenomenon or homogenization phenomenon. And, like, I think it's kind of plausible. It feels like some sort of law of large numbers, like there's a lot of randomness in the problem and it's being averaged out. But we fancy to call this homogenization, not averaging. I think in large measure because A bar is actually not what maybe you would expect at first sight, which would be the expectation of A. So A bar is some averaging of that involves the law of A, but it's not the naive expectation of A. Okay, so A bar, not expectation of A. Okay, it's obtained through some sort of averaging procedure, but it's not the easiest one you could think of. Okay. Okay, and this is a bit the crux of the matter, because at least if A bar was just obtained by simple averaging of A, if the random coefficients are have a finite range of dependence, we would understand quite well how taking averages of these coefficients A bar is more mysterious in some sense, and so it's less obvious how to make this convergence quantitative. Are you here? I see that.
Yes.
Yes.
No, we lost connection, but we got it.
Okay. Sorry about that. So are there other questions so far, or are things okay?
Yeah, it's very clear.
This result with the U and the U bar, it's kind of, I'm not sure exactly, maybe this is some part of the domain, maybe it's some slice of my domain, and this is the value of U bar, and the truth function that I'm trying to compute, instead it's it's a bit affected by the fact that the coefficients are random and are crazily oscillating. So here, the domain is very, very large. So if I draw things to scale, the coefficients oscillate on a very small scale. So I haven't finished my drawing, but okay. And the scale of the oscillations here is the unit scale. Okay, and the domain is very, very large. Okay, and this is what we want to understand in general for arbitrary domains and boundary conditions, etc. But I do this drawing because I want to suggest that maybe if we were to restrict to some sort of intermediate scale in this problem, this function U bar, it solves, A bar, okay, it's not the identity, but okay, up to a change of variables, it's the identity. U bar solves something like Laplacian U bar equals 0. So U bar is a harmonic function. It's an extremely smooth function. So if you zoom into some scale intermediate between the giant scale you care about and the unit scale in which things oscillate a lot, then it's plausible that you can sort of pretend that U bar is actually just an affine function. Okay, it's not quite exact, but it's a good approximation of what U bar is, because U bar is a very smooth function. So in fact, instead of trying to think about all of these general problems with all sorts of boundary conditions, etc., it's enough to just focus on a simple domain of your choice, let's say a cube, for instance, and a situation in which the limit, the U bar, is just an affine function. Okay, if I understand this, then I'm going to be able to then patch this understanding on some sort of intermediate scale and then conclude for general results. Okay, so what I want to say here is that it's enough to understand the situation with U equals a simple domain. I mean, okay, maybe I should not say simple because then it has a specific meaning, but let's say a cube, and U bar and being an affine function. Okay, and then in practice, instead of doing a drawing, we do what is called the two-scale expansion. So you patch these things together in a way which is actually analytically quite nice. You don't even have to do a partition into subcubes and try to understand how to glue them together, etc. You can do it in relatively nice way in some analytic sense.
Yeah,
Okay,
I have probably a stupid question, but if you want U bar to be affine, is it sufficient to take G to be just the restriction of an affine function?
Yeah, exactly. That's exactly what I'm gonna
Okay.
do. So what I'm saying is that it suffices to look at this problem. So let me write this for the cube. Okay, so the cube, I draw a square to denote a cube, and U of x is a P dot x on the boundary of the cube. Okay, where P is some fixed vector we have given in advance. Okay, and this is all I want to understand. Only this this problem. I want to understand what happens to this thing quantitatively, and then once I have understood this, I'm done with my problem. And this is not a cheat. Like I really, it's actually true that once you understand the homogenization for this problem, you can really recover all sorts of more fancy results. So in this setting, what U is trying to do is trying to match the affine function, but it has to accommodate these oscillations of A of x. The affine function itself is not a solution of this equation, because remember, A, I don't write it, but A depends on x. So it's A of x. And you're taking divergence of A of x grad U. So A of x is not divergence free, so this is not going to be a solution. So you're going to have some corrections to, even though U is trying to be like the affine function, it's not going to be exact. So what you're going to have is that U of x is going to be P dot x plus some remainder. Okay, so I'm going to denote it phi p, and maybe I put a little square on top to remember that it depends on the domain I choose of x. Okay, and this object is called the corrector. And what I've been saying is that what we want to know is that the corrector is small compared with the affine part. So what we want is that phi p. Okay, maybe I'm not going to write the superscript with the cube. Okay, is that this phi p of x is very small compared with p dot x. Okay, and maybe just to, okay, do I need to do this? Let me think. Yeah, maybe I can write, no, okay, maybe I skip. I'm hesitating. Yeah, I will skip. And okay, so this is like the PD view on how to understand homogenization, and also geared towards making it quantitative. But if you want to think in probabilistic terms, you can also see this object, this phi p emerging, because, so alternatively, let's say, what these guys provide you is they provide you with harmonic coordinates for your dynamics. So if instead of, so I'm describing a mapping from RD to RD, and so I'm sending x to x plus this this correction, which I'm going to, okay, so on the first coordinate is phi in the E1 direction, and then it's in the ED direction. So this mapping, if you look at your diffusion through this mapping, it is going to become a martingale. And since ultimately we want to say that our diffusion looks like a Brownian motion, it's very good if we can say that it's actually a martingale plus a small error. So when we do this, through this mapping, we can view our diffusion as a martingale, and then we would like to say that this piece that we have added in order to make it a martingale is small. Okay, so again, we see that if we want to show a central limit theorem, the question is about showing this sort of thing. Okay, to say that this extra bit that we have to add in order to transform our diffusion into a martingale is a small bit. Okay, it's smaller than the main contribution, which is the x point. Okay, you see that being a martingale, if I give you a Markov process and the function f then f of xt will be a martingale if and only if LF is equal to 0. Okay, so and we have made it so that x plus these 5 functions are harmonic for the generator. Like they solve the equation. So
Yeah, Christophe?
Yes, Hamilton.
May I ask a question?
Yes.
So you're saying that if you know what happened with these affine functions, then you will be able to more or less get the information you want about this problem. So, but for instance, if you know something about also about quadratic functions, does it mean that you know more about your problem, or no, it's not really?
Yes. In fact, it's like you're uncovering the expansion of your solution, if you want. So it's like you want to do a Taylor expansion of your solution, except that the good affine functions are these functions, p dot x plus the corrections. And then if you want to be even more refined, you want to say that the quadratic functions in your problem, they are, they try to look like a parabola, but there's also a correction. And so you can build also these objects, which are called higher order correctors.
Okay, thank you.
Are there other questions? Yeah, okay, no, maybe I'm not. I'm tempted to do many comments, but yeah, okay, I'll do it. So if you think in the spirit of regularity structures or whatnot, this is like the probabilistic object that you want to build kind of separately. And then understanding your model is more like deterministic transformations of, okay, no, maybe that was not a good comment. Okay, let's close this parenthesis. Sorry about, should not have done that. Okay, so what I wanted to emphasize is that what we really want to shoot for is proving something like this, or at least understanding quantitatively what happens with this problem. And in order to do so, it turns out that it's extremely useful to think about this problem in some variational terms.
I have a small question. When you say p dot x, you mean something like the diameter of your cube, right? What you have
So
on your right side?
p dot x is the affine function. Okay, x is the variable, and indeed, when the cube is very large, the p dot x will be huge at except near the origin, but at a typical point in the cube, because the cube is enormous, p dot x will be well like the length scale of the cube, because x will be living in the cube.
Okay, then there is something I don't understand. Okay, if your cube is centered at 0, for instance,
Yes.
the Phi of x, the place where it will be the largest, it should be 0, right?
Yes. Yeah, so this should be understood in some, okay. But it should be understood, so maybe I should say it's very small compared with the typical length of the cube. Okay, fair enough.
This is what I thought, but I just wanted to be sure that this
that's right. So maybe I'm going to write something like this. Yeah, you're right. Yeah, thanks for this clarification. So it's like, you want to say that the supremum over, it's like ultimately you want to, the reason I wrote it in a different way is that ultimately you can build this phi p even for arbitrarily large cubes, and you can pass to the limit. Maybe you pin it to 0. Okay, this phi is defined up to a constant. Yeah, no, not really, but okay. Okay, sorry, I'm not explaining this well. If you don't care about constants, you can show that this thing converges to something. And so then you would like to talk about this something, which really is what people usually call the corrector. And then you would like to say that when you take the supremum over any, let's say, ball of radius r, the supremum is smaller than, is very small compared to r. And so, yeah, kind of, anyway, yeah, thanks for this clarification. I was not being very precise. Are there other questions? So yeah, I wanted to say next that it's really useful to think about this problem in variational terms, meaning that instead of saying solve this PDE, I can say find the minimizer of this energy function, and the minimizer will turn out to be the solution of the PDE, but it's kind of convenient for reasons I'm going to explain to think about this problem in these energy terms, these variational terms. Okay, so again, I put a 1/2, but this is for my, it's not quotient. Okay, so I look for the function which is, so h10 means I impose the v, like this correction part, to be 0 on the boundary. Okay, so ultimately, the best v will be this phi p here. Okay, so phi p is 0 at the boundary, and I claim that it's just a simple calculation to see that if you look at what the optimizer for this very nice uniformly convex problem is doing, it is this phi p. Okay, and so what I would like to say is that the minimizer of this guy is not very large. Okay, this is just a rephrasing of the problem. And instead of focusing too hard on this, I'm going to first try to understand the value of the energy itself. Okay, like what is the value of the energy doing? The reason it's interesting is that this quantity is subadditive. So like as a function of the domain, this is subadditive. Okay, so let me argue first that this is true, and then I say why it's good. So if you imagine you have a big box and you split it into sub boxes, then you can try to solve this minimization problem in each of the small boxes or on the big box. Okay, and I claim that you can do the following. So the optimizer is 0 at the boundary of the domain. Okay, so if you look at the optimizer in each of the small boxes, their values agree on the common boundary, like here. Okay, they are all 0 here. So you can glue them together and you have a valid function, not something crazy that has a discontinuity. So in particular, when you have glued the things together, you still have a candidate function for the optimization problem in the big box. Okay, and since the problem is an infimum, then you know that the best guy in the big box is going to only be, it can only be better than what the guys in the small boxes have managed to do. Okay, because the guys in the small boxes are you can use them for trying if you want, and maybe the best guy will be even better. Okay, so we see that the energy on the bigger cube is going to be smaller than the average of the energies in the smaller cubes. Okay, and yeah, why is it good? So the difficulty is that our corrector is not a simple function of the coefficients. So we have a lot of nice properties of the coefficients. So they have finite range of dependence, etc. We would like to use central limit theorem, but we don't know how to do that when we talk about the corrector, because the corrector is a nasty object of this coefficient field. No, it's not a local function of this. But here we are recovering some aspects of it because, well, it would be best if nu was additive instead of subadditive. But if it was additive, obviously it's only looking at the coefficients in some local region. And if it was, if you could obtain the bigger one by just adding, like averaging the ones on top, that would be perfect. Okay, then we would understand quantitatively how this converges. All right. So anyway, it's subadditive. It's not hard to see that it's bounded away from 0 and infinity also. And so it's going to converge to something. So maybe you appeal to the subadditive ergodic theorem. But okay, yeah, another thing I should say is that, okay, so let me first say that. Converges. as the cube increases to RD. Let's say you keep the cube centered in the middle. Yeah, and the last thing I wanted to say is that, so I should have said that earlier, but this corrector guy, it depends linearly on P. Okay, if it's an easy verification. And then this thing is going to compute the energy of this corrector. Okay, so it's going to be some quadratic function of phi p. So this thing is going to be a quadratic function of p. Okay, so again, I'm going to be a bit quick. I'm going a bit quick, but it's not difficult to verify that it's true. So this function nu of cube comma p is a quadratic function of p. So if I want, I can write it as, so nu of cube p, I can write it as 1/2 p dot some matrix p. Okay, and this matrix I'm going to write a of cube, like this. And what we say is that this converges. And so in other words, this matrix A of cube converges to something when the cube goes to RD. And this limit I'm going to call A bar. Okay, and this is, you can take this as a definition of A bar and then derive the properties I announced before. Okay, and I'm seeing that my time is running, so let me try to be concise. So, yeah, what's the link between studying this quantity and trying to show that the corrector is not too large? The link is that if somehow there was someone telling me that this quantity is not just subadditive, but actually really additive, then I claim I could deduce that the corrector is small. The reason is that this is a uniformly convex function. Like this energy is uniformly convex in V. So if I tell you that something is extremely close to, okay, so let me take it back. We have seen how to show that this quantity is subadditive. It's by just gluing together the minimizers on the small scale and saying this is a valid candidate for the large scale. But now let's imagine that someone tells us, actually, basically you get the correct energy, you get the correct value for the energy when you just glue the small scale guys together. Because your minimization problem is uniformly convex, in fact, you know that the true optimizer is very close to being the gluing of the minimizers on the small scales. But the guys on the small scales, they cannot be very large because first of all, they are pinned to a cube of a smaller size. So of course here I did a drawing with with only 2 subcubes in the big cube, but imagine you're doing a very fine mesh with lots of cubes. So then this tells you that your corrector is 0 in lots of places, right? And in fact, you know that by some naive bound, you know that the corrector in a very small box cannot be very large. So okay, I'm not sure if I convinced you, but yes.
Okay, just to check if I understood. So what you're saying is that because of this convexity property, basically, if you have something which is close to minimizing, then it's close to a minimizer.
Exactly. Yes.
Okay.
And if I draw a parabola, this is going to be clear. If I draw a parabola and I say minimize it, and I'm giving you, I'm telling you, oh, I picked a number, and you know what? The value you get when you compute the value of the parabola is very close to the optimizer. You cannot be too far from the optimizer, right? Okay, if I put it here, the value will be very large. So it's okay, so it's just a formalization of this. And you see by the drawing, you can see what's the relationship between the deviation of the energy and the deviation from the minimizer. Yes, and so long story short, we have reduced our problem to showing that this quantity is really subadditive in some good way. And yeah, now this is where, okay, I should put ideas in place, but I have still not talked about particles, so I feel a bit bad. But one of the key ingredients is to introduce a quantity which aims to be almost convex dual to the quantity nu. So ideally, we would like to say that, this matrix A of cube is very close to A bar, but A bar is very hard to access to because it's only defined as the limit of this quantity. And so instead, we're going to try to compare it with something else. And this comparison will be an upper bound for the distance between A of cube and A bar. So in some sense, nu is subadditive. So A goes to A bar by going decreasingly. And we're going to try to devise a quantity which goes to A bar increasingly instead, but is also well defined in finite volume. And instead, we're going to try to say that, this sort of, some sort of interval of confidence on A bar that you devise on infinite volume is small. Okay, this is how we approach the problem. And to define this other approximation of A bar, we study this quantity. So I'm going to call nu star the other quantity. Sorry. Okay, so here I fix, I should have written also it's a function of Q. So I fix a vector Q in RD. And just in the same way that the previous problem was imposing a Dirichlet condition with slope P, this problem is a Neumann problem which imposes a flux of Q on the boundary. And okay, so this quantity is also subadditive, but for a reason which is a bit dual to previously. So let's discuss this very briefly. Okay, I'm not going to speak a lot about particles. I apologize for this. So in this case, there is no restriction on your, there's no boundary condition on your space of allowed test functions. So what you can do is take the optimizer in the large box, and you can use it as a candidate in the small box. But because the quantity is the supremum, you know that the quantities in the small scales are going to be greater than the quantity in the large scale. If you average the quantity in the small scale, the number will be greater than the quantity in the large scale. So nu star is also subadditive. And I claim it's approximately dual to nu star to nu. And we can see this because I can try to plug this p dot x plus phi p of x inside this energy, and the true quantity is actually greater. And if I do this plug-in, then I'm going to get so the average of the gradient of the corrector is 0, and this is going to give me p dot q, and then this is going to give me the previous energy, so it's going to be minus nu of cube p. And so you see that this evokes a convex duality. If I could take a supremum over p on the right side, that would be good. And this duality will become exact. Yeah. Okay. So yeah, I'm looking at my time and I'm becoming stressed out. But so there is this. You should think of nu star as trying to be the convex dual of nu, and nu is trying to look like 1/2 p dot a bar p, And so this one is going to try to look like the convex dual of this quadratic function, which is q dot a bar inverse q. So this guy is also subadditive, but it's trying to look like the quadratic form with matrix a bar inverse. So that's why I'm saying that it's progressively approximating a bar from below, because it's approximating a bar inverse from above. Okay. And I would have to explain how we approach this, but we have some approach that allows us to compare directly, try to assess the quality of this convex duality defect, to try to say that in the regime of large scales, the nu star indeed becomes almost the convex dual of nu. Okay, and this is actually easier than trying to relate nu to its limit directly, because comparing nu and nu star, both things are defined in finite volume, so we have a better chance to do that. All right, so yeah, the end of the story was quite short, but maybe I can say just 2 words on particles. So yeah, the thing next is that we want to see if this sort of strategy can be adapted to talk about interacting particle systems. And yeah, so okay, I'm kind of running out of time, so I'm not sure how best to proceed here, but let me describe the model that we treat at least. So it's a cloud of particles. So maybe one could, if we think about the stochastic process, we could maybe encode it like this, like maybe a countable, or maybe let's say a finite or countable number of particles. Let me just write capital I for the index set that evolve in time. And we would like that each particle performs a diffusion in the spirit of the diffusion environment we have seen earlier, except that this diffusion matrix this time is not fixed and frozen in the environment. It's a function of how the particles around the particle we're talking about look like. Okay, so we would, yeah, and because we want to stress that the particles are not distinguishable. They don't carry a label that, like you cannot say, oh, this is particle number 15, I've seen it earlier. Okay, we don't want you to be able to say such things. And so instead of encoding the dynamics as a list of particles that move around, we put everything into a measure, and we say that we study the evolution of the measure. So the measure, you should think that it's the sum of Dirac's, and the positions of the Dirac's are the position of the particles. So maybe it would be mu of t, but okay, maybe I just write mu delta xi. Okay, so this would be encoding a configuration where the particles are located at xi. Okay, and then the diffusivity matrix is A of mu and x. And this we assume is stationary, which means that if I shift the cloud of particles towards the origin, let me denote like this the measure that is shifted, then this is the same calculation. Okay, so this is a cloud of particles described by mu, and then the diffusivity at position x, and I claim that I want my function A to be satisfying this property. I also want it to be finite range, so I want to be able to compute the diffusivity matrix by only looking in some neighborhood of the position I care about. So let's say it's sufficient that I look at the restriction of mu to B1. Okay, this is my notation for the restriction of mu to the unit ball. And I also want a uniform ellipticity as before. Okay, so maybe an example, A of mu and x is, let's say, 1 plus the indicator function that there is at most one particle in the, so I should write 0. Otherwise, I would have to shift it. And this is times the identity matrix. Okay, so this would give you a particular diffusivity depending on whether or not your neighborhood is crowded or not. So maybe in the long run you would like rather to model balls that bounce against one another, but here we are not able to consider this sort of setting yet. So we just say that maybe, as an example, maybe the diffusivity is going to change if your neighborhood is crowded, but it's never going to 0. It's always bounded away from 0. And yeah, I'm out of time. So let me just say that in this setting, it took us, so with Arianna Giunti and Chenlin, we spent some effort trying to see if we could identify quantities that look like those I described for the random walk in random environment. Again, the requirements are something that's some sort of energy quantity that would be subadditive, that would be defined in finite volume, that I could compute in some sort of bounded domain, and that would be a good approximation for A bar as we go to infinity. And also to find some dual quantity that looks like the new star I introduced for the random walk in random environment case. And once we have these two things together, see if we can indeed do this game, which I have not had time to describe, of comparing one against the other in order to get a quantitative estimate. And so, okay, I have not described it precisely, but let me at least state a theorem. So, which is with Giunti and Gu. So we can define so matrix A of cube analogous to the random walk in random environment setting. And we can show that there exists, let's say, a constant and an exponent such that this matrix minus its limit, which we can still call A bar, is bounded by some constant times the size of the cube to the power. Okay, so it's still a relatively not very explicit rate. Okay, we have just managed to show that there exists an exponent, which is strictly positive, such that this occurs. But this was also our first step when we were dealing with the random walk in random environment. So as a first step, we showed that there exists an exponent such that this is true. And then we used the existence of this exponent to improve this exponent over and over again up until we reach the optimal exponent. So this is what we have for now. And in analogy with the random walk in random environment setting, I hope that is going to allow us to prove more quantitative results, like maybe state a quantitative version of the hydrodynamic limit or other things. And maybe also, if we are optimistic, maybe we can also try to look for ways to improve upon this exponent progressively and get the optimal exponent. All right, so sorry for being over time, and thanks a lot for your attention.
Thank you, Jean-Christophe. And now, if you have questions, well, you can just open your mic, and if there are too many people.
Just to see if I understood, in your theorem, A of the square, is it a random object or a deterministic one that you get when you reduce your problem to the small cube?
That's a good question. And indeed, here the analogy with the random walk in random environment is not good, because in the random walk in random environment, it was indeed a random quantity. because and it depended on the coefficient field in the cube. But here, because of the model, the way the model behaves, basically, if you want to do your integration by parts, you have to take the expectation. So here, in fact, this quantity nu that we define is more analogous to the expectation of the RWRE quantity. Yeah. So here, in fact, these are deterministic quantities.
I will ask a question waiting for somebody else to. Yes, you say that you have the corrector. If you pin it at 0, then it needs a limit when you send the boundary of the cube to infinity. So what's the growth of this limit?
Yeah. So in fact, this is exactly what you quantify when you. So a priori, you only know that it's sublinear in some. And the way you even make sense of what sublinear means is relatively weak, some sort of L2 sense. But after you have done all the theory of quantitative homogenization, you at the end of it, you know a lot about the growth. And in fact, what we have shown in the RWRE setting, like for elliptic equations with random coefficients, is that over large scales, the corrector basically behaves like a Gaussian free field. So then, I'm not going to tell you the growth of the Gaussian free field, but
okay. So when D is larger than 3, you don't need pinning.
Exactly, it's going to be bounded. Yes. And in dimension 2, it grows like a square root of log, and so yeah, all of this is true. And it does rescale to a Gaussian free field. So in fact, you have to extend, you have to enlarge a bit your definition of Gaussian free field. But once you have done that, you can show that the scaling limit of the corrector is the Gaussian free field.
The enlargement is you replace your Laplacian by another diffusion, or something?
It's more subtle than that. So yeah, I can talk about this. So it's still it's a Gaussian field. It has the same type of homogeneity as the Gaussian free field, but it's a little bit more funny. So yeah, if you want, I can spend a few minutes, but maybe like, are there other questions on this talk, or otherwise maybe for those who are interested, I can describe this this funky Gaussian free field.
It seems that everybody wants to hear that.
All right, very nice. So here's my definition of Gaussian free field. Okay, let me think about it for a second first. Okay, so let's say that we want to define it as a generalization of Brownian motion to higher dimensions. So in dimension 1, Brownian motion is that thing whose gradient is the white noise. Okay. So now I want to define a random field in dimension 2 or 3 or higher, which mimics this definition. So maybe I would like to say, oh, I want a field whose gradient is white noise. Now the problem is that this doesn't make sense, because white noise is not a gradient field. So you cannot say, oh, I want something whose gradient is white noise. And in fact, yeah, even if you were doing it in 1D but on a circle, you cannot impose that something, like anyway. So not everything is a gradient. And it's not because it's rough, like, it's just that if you want something to be a gradient, it has to satisfy some special properties. So the next best thing you can do is say, oh, I'm going to take white noise and I'm going to project it onto the space of gradient fields. And then this will be, this will be the gradient of the object I want. So, and if you want to do that, so, if you do some L2 theory, then you can decompose L2 vector fields into gradient fields and solenoidal fields, like fields which have zero divergence. So let's call W your white noise. And I want to decompose white noise into a gradient plus a solenoidal part, and let me call it G, something which has divergence 0. Okay. And then I'm going to call phi our Gaussian free field. So I can do this. So here W, it's a white noise, but it has a D components. Okay, it's a vector white noise if you want. It has D components. So G has divergence 0. So if I compute the divergence of this equation, I get divergence of W equals Laplacian phi. Okay, and this is a nice equation. I can solve it. Okay, white noise is rough, but these are linear equations, so you can solve them, no problem. And so this defines for you a phi, and this is my definition of Gaussian free field. Now this is really just the normal Gaussian free field actually, but here is one funny observation. So here implicitly I assume that so W, I told you it's a vector white noise. Okay, so you should think it has D components, each of them being a white noise field. And so it's white noise, so it means when you change from one place to another, it has no correlations. But at least in principle, you could imagine that the coordinates themselves are correlated. Maybe, for instance, you could take you could take one W1 and then just copy it on the D components. Or maybe you could take independent white noises. So implicitly here, I was assuming you take independent white noises with the same variance. But in fact, there is a matrix of covariances that describes the space of all possible choices for the white noise vector. Does that make sense, what I'm saying? You see that if I take independent copies or if I copy W1 each time, it's different things. Okay, and so there is a covariance matrix hidden there. And separately from that, there's also, here I took Laplacian, but there's also a matrix that you can choose here. You don't have to do your orthogonal projection with respect to the normal scalar product. So perhaps the most general equation you could think of would be, and I'm going to use A bar as a notation for some matrix I could insert in there, is this. Okay, while remembering that you have also a matrix of choices for this W. Okay, W, you can choose a variety of different W's. You can choose a matrix there to describe the law of W. I'm struggling to say it, but and so then you can say, okay, but this is just, I can do a change of coordinates. This is just Gaussian free field. What is he talking about? But the thing is that I want to stress that there are two matrices in this game. And with the change of coordinates, you can only fix one of these two matrices. Okay, so in fact, so what happens here is that if the matrix that describes, let me call it Q. Okay, so there's this matrix which describes the covariance structure of your white noise vector. And there's this matrix A bar. And if A bar and Q are multiple of one another, then you have a standard Gaussian free field. But this, in fact, it's an if and only if. Okay, otherwise it's just a different field. So it will have the same homogeneity, but it's a different field. And in particular, it no longer has the spatial Markov property. The fact that if I tell you the value of the Gaussian free field on the boundary of a domain, then you can resample the inside of the domain consistently. So this domain Markov property is true if and only if A bar and Q are proportional to one another, something we proved with Yugu. And the limit of the scaling limit of the corrector is that object. And it's really that object. Like it's not that we missed some property that makes it be the Gaussian free field. So we also showed that the bizarre Gaussian free fields do occur for certain models. Okay, so I don't know if this clarifies. So then now this is what the generalized Gaussian free field is. If you want to, I was a bit quick, but if you want to read about this, we talk about this in our book on homogenization, chapter 5. And also we wrote down a heuristic derivation of why the corrector is going to solve this equation, which I think is not very hard to read. So if you want to have a look, just some chit chat that explains why this equation is going to show up.
Great, thanks.
What is the reference for your book?
So it's called Quantitative Homogenization, and okay, the title is long, but I have only one book, so it's okay. And it's with Armstrong
It's
and
only
Christie.
your the author. Okay, I will find it. No worries.
The web page of Nation is working. Your website is working, so we can find your book.
Yeah. I haven't migrated it yet to Lyon. But, yeah, it's this one. My web page.
Okay, so if we have no more questions, we can thank Jean-Christophe again. Okay, so thank you for this very nice talk and nice piece in the end with about the Gaussian pressure. And
Thank you very much.
Yeah, we have a meeting next week at the same time.
Well, thanks a lot for the invitation. It was a pleasure to see you.
Hi, Jean-Christophe. Oh, sorry.
Bye.
Yes.
Could I ask you a question? So from the beginning, you define the model that is S dependent, right? So
That is what dependent?
from the beginning, you define the model in the discrete setting that's on ZD. That is
Yes.
S dependent.
That is what dependent?
Edge.
Yes. It's on, yeah, the randomness is on the edges.
So in this case, when we go to the continuous setting, then this A is symmetric.
Correct.
But if you change it to be a vortex dependent, that is to say that a particle is jump to the left or right, it depends on the vortex, not on the edge. In this case, the A, when you go to continuous setting, then A is,
so are you asking what is the correspondence of, so in the discrete setting, I said that we can assume these random variables are independent. And are you asking what's the correspondence in the continuous model?
yes. For the
So
continuous
here you cannot really say it's IID because it's a continuous field. But what you can say is that it has a finite range of dependence, meaning that if I show you, if I take two subdomains and they are at distance, let's say at least one from one another, so then revealing the family of coefficients in the first domain or in the second domain will be these two families of coefficients will be independent random variables. Mm-hmm. So instead of IID, you say finite range of dependence. Any family of variables which are separated by some distance, they are independent families.
But in this case, do you have some kind of corresponding result?
Some kind of what?
This corresponding result, I mean, you change it to be a vortex dependent, not S dependent. You still have this kind of very good estimate. Just look at the collector.
Yeah, no. The critical aspect is to make sure that the counting measure is reversible for the dynamics. But if you want, you can put the critical properties are whether or not you have preserved the structure of the model, which is in the continuous is this divergence form. In the discrete is the fact that the counting measure is reversible. The jump rate from X to Y is the same as the jump rate from Y to X. But in order to satisfy this property, if you want, you can attach the randomness to the sites. That's also fine. You just, for instance, you can say the jump rate is the sum of the randomness you have attached to site X and the randomness you have attached to site Y, or the minimum or whatever, any symmetric function of your starting point and your target point.
Okay.
And then if you have finite range of dependence, everything will be fine.
So A is symmetric. This is crucial for your analysis.
You can also do it what is the symmetry is that the generator is okay. The crucial fact, the crucial thing is that it's in divergence form, that you can do integration by parts. Okay, that's what you want to make sure you keep, because there are only two things I know how to do: it's integration by parts, and I forgot what's the other one. Cauchy-Schwarz, maybe.
Okay, thank you.
So I need to do integration by parts, but in fact, you can even allow A to not be symmetric if you want, as long as you can still do integration by parts. And I want it to be in divergence form. That's the critical point.
Okay, thank you.
Okay, so thank you again, Jean-Christophe. And
My pleasure.
see you soon.
Thank you.
Yeah, see you. Bye.